In this video, we're going to start talking about the second big question in calculus. If you remember, the first big question is how do you find the slope at any point on a curve? In this video, we're going to start talking about how do we find the area under a curve. So we're going to start with this. Mr. Anderson starts walking at a constant velocity of 4 feet per second. How far has Mr. Anderson traveled in 10 seconds? Well, I'm going to make a little velocity graph here. So we're going to put velocity. We're going to put time. So I put like 10 over here, and maybe put 4 right here. Of course, it's constant, so it's just going to be a horizontal line up to 10. Now, if you think about this, you say, well, 4 feet every second for 10 seconds. He's gone 40 feet. Well, I like to think about this in terms of geometry, and I think, hey, 40, that represents the area of this rectangle. Okay, well, that's not a coincidence. The area under the velocity graph will give us the total amount of distance, or total amount that he's traveled here. Mr. Morris walks so that his velocity is modeled by this equation of 0.5 t, where t is time in seconds. So now it's a little different because it's not a constant. We're still wondering about, 10 seconds, so I'll put that here. Now, this 0.5 t, at time 0, that means he's going 0, and at time 10, he's going 5. So let's put 5 here. And of course, it's linear, so it's going to look something like that. So now, how far has he traveled? Well, we once again are thinking area. So we're going to find the area under this triangle. Well, of course, area of a triangle is 1/2 the base multiplied by the height. So Mr. Morris has walked 25 feet. Now I want you to just think about something for a moment. I'm just going to kind of write this just down in the corner. Before, when I gave you position or distance, an equation, we usually wrote that as S of t. And I wanted velocity. Okay? And I wanted velocity. I'm going to put that right here. How did I get there? Well, I took the derivative. Okay, I did the derivative of s with respect to time. Okay? And that gave me velocity. Well, now I'm giving you the velocity, and I'm asking you to work back to position, or where the person is in relation to where they started. And there's got to be a calculus way of doing it. I just want you to kind of think about that as we proceed forward. All right, Mr. Danielson, always the fastest but most complicated, starts walking at a velocity that's measured by that equation. How far has Mr. Danielson traveled in 10 seconds? Well, this is the graph. And again, it's an always positive velocity, but at varying amounts of positive. So I never changed direction, but you're going not starting at 0, then going really fast, then slowing down a little bit, almost 0, and then speeding way up. Well, there is a calculus way to do this, but I wanted to focus on how this was done before we really understood how to do it with calculus. So it was done before with rectangles. Okay, so I'm going to start by drawing rectangles. And you'll notice that some of them are overestimates, some of them are underestimates of the actual area. For sure, those first couple and this last couple, the rectangle area is way bigger than the actual area under the curve. Okay, this is what's called a right-hand estimate or right-hand sum. And the reason it's called a right-hand is because we've drawn 10 rectangles, 0 to 10. So the first rectangle extends from 0 to 1, and 1 set the height. The next rectangle stretches from 1 to 2, and 2 set the height. So as we're looking at area, as we're looking at area, we say, well, it's got a base of 1 and a height. Well, we've got to figure out what the y value is. So you go, and I took this off my calculator. The y value at 1 is 7.3. So that's the area of the first rectangle. Well, the second rectangle, width is still 1, the height is 10.2. The next rectangle, the height is the width is 1, the height is 9.9. And of course, once you've started calculating these rectangles, I'm just going to do that, then we just add them up. And this would give us an estimate of the total amount of area under the curve. And again, it's just an estimate, but it could probably be a pretty good one. Now, I want to draw another set of rectangles. Okay, this time I'm going to use the left side to set the height. So again, you've got some underestimates, you've got some overestimates. But now I've let the left-hand side. These are called Riemann sums. Riemann was a mathematician that really studied these and how we could use these. But now, as we find the areas, of course this first one has a width of 1, but the height is 0. The next one has a width of 1 and a height of 7.3, because the left-hand side is setting our height. And again, we'll just add these up. Okay, and that would be our left-hand sum. Now some people say, well, once you've done that, it would be really handy to just average them. And it would. That wouldn't be a bad idea. But there might be a way to get an even better estimate with not having to do both a left and right-hand sum, but instead just doing one sum and not having to average it. So I want to focus on that next. So now I still want to go from 0 to 1. But instead of letting the left hand 0 or the right side 1 set the height, I'm going to let 0.5 set the height. Like that. As I extend from 1 to 2, I'm going to let 1.5 set the height. 2 to 3, I'll let 2.5 set the height. So I'll always use the middle of the interval. Now hopefully you look at this and you say, well, I can see why that would be the best estimate. There's no question that, compared to the left and right hand sum, your overestimate, underestimate is going to be better. And again, your width is still going to be 1, but how will you get the height? Well, you'll actually have to plug 0.5 in. And, it'd be just as easy as going to your table. I made this table with my calculator. You could certainly just go to your table and change it to start at 0.5. So 1.5, 1.5, 2.5, and gave you all of those. I'm not going to do that right now, but, that's all it is. You're letting the middle of each interval set the height. And this is called a midpoint Riemann sum. Okay, the midpoint. Now, I just want to introduce some quick notation here, and it's not even really going to be great correct notation, but what Riemann was working under is that an x value, the width, you'd multiply that by f of x. This would give you your rectangle, right? This would be your base, this would be your height, and essentially you would just add these up at the end. That's really the idea behind the Riemann sum. And he said, well, if I could do more and more of these, if instead of 10 rectangles I did 20 or 30 or 100, then I'd get a better estimate. So essentially, the limit of this, if you were willing to do just an infinite number of rectangles, okay, so n is the number of rectangles. If you had an infinite number of rectangles, you would reach the actual area under the curve. Now again, notationally, nothing I've written there is really all the way correct. I just wanted to give you the idea of what was happening here, and that is the fact that if we could introduce more and more rectangles, we get closer and closer to the true area, so it kind of connects back to the idea of a limit.